All right, Bismillah. So let's get started. So this is today's the last part 3 of chapter 8, and we'll talk today about membrane transport and receptors. And we've started talking about membrane transport last time. So just very quickly, we said there are two types of transport. Primarily, you have what's called passive transport, and then you have active transport. And we said passive transport, you have two types of passive transport. You have the simple diffusion, and then you have the facilitated diffusion. And the active transport, we didn't talk much about it, but we have two types as well. We have the primary active transport, and then we have what's called the secondary active transport. So coming back to passive transport, we said passive transport is the hallmark, or when you have passive transport is when you're driven by a concentration gradient, so meaning from high to low concentration, right? So, and this is of course makes sense, and this is basically the same thing as osmosis, osmosis as well. And you have simple diffusion where a molecule or ion moves through an opening, right? This could be semi-permeable membrane or small pores it can go through. Or you can have what's called, so this is simple, or you can have what's called facilitated diffusion. And the word facilitated means helped, something is helping it, and in which the molecule or the ion is carried across the membrane by a channel protein, right? So it's not just something linking to the membrane. No, rather there is a channel protein which is helping it, which is facilitated this, and it is from high to low, right? And this is the hallmark of a passive transport. Notice there is no energy being used, it's just high to low. It's driven by concentration gradient going down a concentration gradient. The opposite to that is what's called active transport. In the active transport, again, the hallmark is that the substance is moving against a concentration gradient. So it's going from low concentration to high concentration, right? So this is just the opposite to high concentration gradient. Okay, and it is linked to hydrolysis of ATP. It is linked to energy usage, ATP usage, right? Um, so this is called primary active transport. The other flavor, which is called the secondary active transport, this is basically something which is linked. So it's driven by primary by proton gradient. So um, for secondary active transport, you have two parts to it. One part is the primary, which is this guy, and second part is the proton gradient, which is generated by primary transport that is used to move ions. And we'll see this in more detail, and it'll make more sense. Okay, so again, passive transport, it is dependent on the concentration, um, or a carrier protein. So if you have, for example, something just going down the gradient like that, from high to low, for example, right? So this is high, for example, and it's low inside. This would be example of simple diffusion, simple diffusion, right? But if you have a carrier protein, right? This is a carrier protein or a pore or something, then this becomes, if that is the case, so simple diffusion, and if you have carrier protein, this becomes facilitated diffusion. And the example is how glucose, which is high in blood, goes inside a red blood cell, which has less than 5 millimolar, and it goes down a gradient through a pore, right? This is an example of a facilitated diffusion. Okay, now again, active versus passive. In passive transport, you have high to low diffusion, or you have pores, which is facilitated diffusion. But again, even in the case of facilitated, you are going from high to low always. So that is always the case in passive transport. In active transport, we said again, we're going from low to high. So you have 2 here, and you have 5, for example. So it's going from low to high, and this is driven by ATP hydrolysis. This is going against a concentration gradient from low to high, and is driven by ATP hydrolysis. Okay. Now, active transport again. This slide is actually a bit complicated. This talks about the sodium potassium pump. We talked about this last time. Um, I think a couple of weeks ago. But so don't. So this is just read this, please, but don't memorize this. This is kind of scary and confusing. I have put a better one, which is similar to what you've seen before, which is this one here, which again we know that sodium. So if you have in the cytoplasm, you have low sodium, it'll bind to the sodium potassium pump, and binding it doesn't mean anything, it just binds to it. But then when ATP comes along and ATP hydrolysis occurs, there is a conformational change, and whatever sodium is bound is eventually released once the pump is phosphorylated, and then in the phosphorylated state, potassium, which is again low outside and high inside, is able to bind, and binding again doesn't do anything. It's not released till the phosphate is released, is hydrolyzed by water, right? And that happens, which allows the potassium to come inside, right? So this is again the sodium potassium pump. It is driven against the concentration gradient, and it's linked to the hydrolysis of ATP. So please make sure you understand this as well and memorize that, but not the previous slide. Just memorize this slide. Okay, so just to summarize, what types of transporters we have either simple diffusion or we have facilitated diffusion. These are examples of passive transport. So this would be passive transport, right? Or you can have active transport, and the active transport, again, you're going against a concentration gradient and is driven by ATP hydrolysis. And this is called the primary active, but you also have the secondary active, and we'll see this in a bit more, right? Or you can have ion channels or ionophores. So we didn't talk about ionophores, but ion channels again is by electrochemical gradient, and this is very similar to to secondary active transport. So this is active transport is here, and this is also active transport, right? So just don't worry about the ion channels, or don't worry about the ionophore. But ion channels, if it is going down a gradient, then of course this is facilitated. If it is not, then it is not facilitated. If it's linked to H plus, for example, then it will be secondary. If it is not linked to it, H1, it could be, so this could be here or it could be here. So it could be here as well, depending on what is happening here. But so just know the passive and the active ones that I've talked about here. Okay, now for the active transfer, as I said, it goes against the concentration, so you have low amount here, and you're going into high, right? So against the concentration gradient, and ATP hydrolysis is occurring here, right? So this is again an example of ATP hydrolysis, an example of active transport. So you can have, of course, this is the primary active transport, but you have the secondary active, and I said secondary. What happens is you go from, for example, in this case, you go from high to low. So for example, so these guys are, S1 is here. You go from, sorry, low to high, not high to low. So go from low concentration to high concentration, right? And ATP hydrolysis takes place. This part is the normal. So this part here is the normal primary transport, right? Primary active transport. Now what happens in the secondary active transport? In the secondary part, what happens is, so this is the first primary, right? You use the concentration gradient that you've established. So going from low to high, it makes a lot of these guys, and then these guys goes down a concentration gradient, right? So this could be H plus, for example, or could be some other things. Once you establish an H plus gradient, it goes down, and as it's going down a gradient, it takes along something against a concentration gradient. Right? So again, there are two parts to it. The first part, we use active transport to create a gradient, right? ATP hydrolysis, and then this high gradient of H plus, for example, or something else, it goes down from high to low, and as it's going down, it takes along something else with it against a concentration gradient, and that's called the secondary transport, right? So I think this is a bit explain a bit more here. So in secondary active transport, the movement of a driving ion down an electrochemical gradient, right, is used. So this could be, for example, H plus, right? You've created a lot of H plus. Could be used to drive the uphill transport of another ion or molecule against its electrochemical gradient, right? So that's the active transport. There are two kinds of them. There is what's called the co-transport. Oops, address that. So there's something called there are two types of it. There's co-transport, right? And then there's also called the anti-transport. So let's see, co-transport. So co-transport on import and exchange. Yeah. So or exchange. So you have co-transport is called symport, or you have antiport. So in the symport, they both go in the same direction. Co-transport, they both go in the same direction. But again, what you do, please make sure you understand this. So you use ATP hydrolysis to go from sodium from low to high, right? So this is active transport. ATP hydrolysis is used here. Once you have made a lot of Na plus or H plus or other ions, then this goes down a gradient. This goes down a gradient from high to low, right? And then it can take something else. So here it is taking, a little bit of X, it's taking X inside, right? So this is called in the same direction. This is called symport or co-transport. Or you can have high to low again. So this is secondary transport here. This is secondary transport, low to high. But then in this case, you have opposite direction, right? And this is called antiport. So it's all explained here. So please make sure you understand there are two types of secondary active transport: symport, which is in the same direction, or antiport, which is in the which the flow is opposite direction. Okay, so the last part really is what's called membrane receptors, and remember in the we've talked about how in biological membranes you have proteins, integral membrane proteins. Some of them are receptors, some of them are channels, and so on and so forth. And so in terms of receptors, the idea really is this: that you have this biological membrane, right? You have some proteins. In this case, this is the protein, integral membrane protein, right? And this protein is a receptor. What that means is something is signaling molecule, or we call it a ligand, right? Same thing as signal molecule. Could be a hormone, for example, like insulin could bind insulin hormone. Could be other hormones, for example. So these guys will go and bind to a receptor, and once it binds to a receptor, this is called reception. Once it binds to the receptor, there is a conformational change, right? There's some change, structural change, or conformational change that occurs, and that allows some other proteins or something else to become activated. So this is called activation of proteins, activation of enzymes, enzymes or proteins or something, enzymes or other or something else. And when this thing happens, um, uh, this is called the signal is being relayed or signal is being transduced. So um, you have signal reception, then you have signal transduction, right? So this is signal binding to it, and then this is signal being transduced, and then at the end this will lead to a specific activity or action, or a change inside the cell, and that's called the response, right? So this is called response. So you have a signal binding to it, and then eventually something happens at the cell, and then you have a response. And response could be like cell movement, for example. Cell starts moving away, cell movement, or cell growth, for example, cell growth, right? Or Apoptosis, we talked about this last time as well, apoptosis. So if a cell needs to die, for example, a signal is received, something happens in the cell, and then the cell has a response, which is apoptosis. This is a general scheme of what's called signal transduction, signal transduction, or how cell signaling occurs, transduction, or cellular signaling, how signaling occurs inside the cell, right? So it turns out, if you look at receptors, there are 4 classes of receptors. The first class is called a receptor, which is also a channel. So it's a integral membrane protein. It's an ion channel, or it's a channel. And when a ligand, when a hormone or something, this is the ligand, when it binds to it, and then binding of this will cause again a structural change. So we call it structural change occurs, and it allows the ions to go through back and forth, right? Which allows the ions to go through and opens up the channel. So ligand binding opens or closes the channel, and then you have ions moving back and forth, and that would lead to cell movement. So a lot of the neurons in our body work like this. So ion, there's potassium, sodium, or calcium movement, and causes the muscle movement. All those things happens by this. Okay. The second approach is called a receptor, which is linked to an enzyme. So this is receptor linked to a channel. This is receptor linked to an enzyme. So this dash means linked. Okay. So in here, what happened again? A ligand binds to a receptor. There's a conformational change that happens here. Something happens here, and that allows this enzyme to be activated. So enzyme becomes active, right? So there's a conformational change. So ligand binding to an receptor enzyme activates the intracellular enzyme, and the enzyme is activated, it will have an effect or something happens. A response occurs. The third type of receptors are receptors. This is a receptor that are linked to a protein, and these proteins are called G protein. These are specialized proteins. So ligand binding, again, this ligand binds to it. There's a conformational change that occurs here. It leads to this G proteins becoming activated. So it leads to activation of G protein, right? And then they do something else. So ligand binding to a G protein coupled or G protein linked receptor opens an ion or alters enzyme activity. So these guys will open an ion or will make things active. The fourth kind, and this is the last kind we'll talk about, is a ligand. A ligand binds to a receptor, and this receptor is linked to the cytoskeleton. Remember, we talked about cytoskeleton in the membranes. So ligand binding to integrin receptors alters the so this is integrin receptors, changes the cytoskeleton, so the cell shape would change or something else will happen. So again, binding of ligands or cell signals or hormones can cause 4 different effects. It can activate open ion channels by receptors that are linked to channels. It can activate different enzymes that are by binding receptors that are linked to enzymes. It can activate G protein by binding to receptors that are linked to G proteins, and G proteins will cause other things to happen like ion channel or enzyme activity. Or we can cause a cytoskeleton being changed by the signal binding to integrin receptors that are linked to the cytoskeleton and changes the cytoskeleton. Okay, so now this is the last slide, and I really, so I'm not responsible for this. So I just want you guys to know that you're not responsible for this, but please watch it. Please watch it. It's extremely educational. You will learn a lot of things, especially those of you who are interested in medicine. It really would it talks about the overview of signal transduction, and colors keep changing. What they're saying is, so if you're a person, you see an angry bear coming running towards you, right? What happens? Well, so that is the visual cue, and that is the signal. So the signal is you're seeing something, angry bear coming running towards you. What should happen? There should be some signal transduction, and the signal is transduced or passed on to the leg muscle. And what response do we see? Well, the response is run for your life, right? Run, right? And this is again all done by cell signal transduction, and this link actually talks about that. So please look at the link, and you'll enjoy it, inshallah. All right, I think this is it. I'll stop here, and inshallah we'll see you tomorrow. Assalamu alaikum.